On average, every star in our galaxy hosts at least one planet. That is not a poetic guess. It is a statistical conclusion drawn from observations of over 150,000 stars. Multiply that by 400 billion stars in the Milky Way alone, then multiply again by 2 trillion galaxies in the observable universe, and you begin to approach a number so staggering that the human brain quietly refuses to process it. We are not unusual in possessing a solar system. We may be unusual in other ways, but the sheer abundance of worlds that must exist in the cosmos is no longer in serious scientific doubt. What is still in serious doubt is our understanding of scale. Not because the measurements are imprecise, but because the distances involved so completely outstrip the spatial reasoning. Our brains evolved to handle that the numbers slip past us like words in a language we do not speak. This is a story about scale. It begins at the size of a human body and ends at the edge of everything we can observe. Every step along the way will demolish the intuition you built at the previous step. That is not a rhetorical promise. It is what the measurements actually do. You are roughly 1.8 meters tall. Your brain uses that height as a baseline for every distance you have ever navigated. The hallway to your kitchen, the walk to the nearest shop, the drive across a city. Evolution built your spatial intuition for a world measured in footsteps and throwing distances. Your ancestors needed to judge the gap to a water source or the width of a river crossing. They did not need to comprehend the distance to a neighboring star. And so the brain that was handed down to you contains no machinery for doing so. That limitation becomes important very quickly. The tallest structure humans have ever built is the Burj Khalifa in Dubai, standing 828 meters above the ground. If you stood at its base and looked straight up, your neck would crane and your sense of proportion would already begin to wobble. Stack 450 people head to toe, and you approximate its height. By the standards of everything your brain has processed in daily life, 828 meters is enormous. Mount Everest rises to 8,849 meters above sea level, more than 10 times the height of that building. Climbers who reach its summit describe looking down at the clouds and feeling the faint visible curvature of the Earth on the horizon. The atmosphere thins to the point where survival without supplemental oxygen becomes a calculation measured in minutes. Hundreds of people have died attempting that summit. Thousands more have returned with permanent damage to their bodies. By any human standard, Everest is the most extreme environment accessible on foot. Yet Everest is a surface blemish. If you shrank Earth to the size of a billiard ball, the mountain would be invisible. The planet would actually be smoother than a standard billiard ball, which contains shallow dimples that, at Earth scale, would represent features taller than Himalayan peaks. Earth measures just under 12,756 kilometers in diameter. If you drove a car straight through the planet at highway speed without stopping, the journey would take roughly 5 days. The circumference at the equator stretches approximately 40,075 kilometers. A commercial airliner cruising at nearly 900 kilometers per hour would need a little over 45 hours of continuous flight to circle the globe once without landing. 2 days in an aircraft, and you have wrapped around an entire world. Your brain can almost hold that. Now leave the surface. The International Space Station orbits Earth at an altitude of approximately 400 kilometers, completing one full lap of the planet every 90 minutes. Astronauts aboard it are moving at roughly 28,000 kilometers per hour. From that altitude, Earth fills most of the view. Continents drift past beneath them. Storms spiral across blue oceans. The planet looks vast and impossibly alive. But the station is barely above the atmosphere. If Earth were a basketball, the station would orbit less than 6 millimeters above its surface. You would need a magnifying glass to see the gap. That is how close humanity's permanent presence in space is to the ground. The moon changes everything. It orbits at an average distance of 384,000 kilometers, roughly 30 Earths placed side by side. When the Apollo astronauts traveled there, the journey took approximately 3 days. 3 days of coasting through absolute emptiness, Earth shrinking behind them, the gray cratered moon growing slowly in the forward window. Radio signals between mission control and the spacecraft experienced a delay of about 1.25 seconds in each direction. When you make a phone call across a city, you expect an instant response. At the moon's distance, the speed of light already introduces a pause you can feel. 1.25 seconds for a question to arrive, 1.25 seconds for the reply to return. A nearly 3-second round trip. That is only the moon. the nearest object in the sky of any significance. The Sun sits approximately 150 million kilometers from Earth. Astronomers call this distance 1 astronomical unit, and it serves as the standard measurement for everything within our solar system. If you drove a car toward the Sun at 100 kilometers per hour without stopping, the journey would take over 170 years. A commercial jet traveling at 900 kilometers per hour would need roughly 19 years of uninterrupted flight. Light, the fastest thing in the universe, needs 8 minutes and 20 seconds to cover the distance. Every time you look at the Sun, you see it as it appeared more than 8 minutes ago. If the Sun vanished right now, you would not know for another 8 minutes. The Sun itself is almost impossible to visualize from inside our intuitive framework. Its diameter spans 1,392,000 kilometers. You could line up 109 Earths across its face. Its volume could contain approximately 1,300,000 Earths. It accounts for nearly 99.9% of all the mass in the solar system. Jupiter, the largest planet, a gas giant so massive it could contain all the other planets combined, is still roughly 1,000 times less massive than the Sunday. Earth orbits a furnace so dominant that everything else within its gravitational reach is a rounding error by comparison. But the Sun's gravitational reach extends far beyond the familiar planets. Mars orbits at an average distance of 228 million kilometers, approximately 1.5 astronomical units. At its closest approach to Earth, the gap narrows to about 54 million kilometers. Even at that minimum distance, a radio signal traveling at the speed of light takes roughly 3 minutes to cross the void. Mission controllers sending commands to a rover on Mars must wait between 6 and 44 minutes for a round-trip signal, depending on where the two planets sit in their respective orbits. The rover cannot be driven in real time from Earth. It operates autonomously, making decisions because real-time guidance is physically impossible across that distance. Jupiter orbits at 5.2 astronomical units, approximately 779 million kilometers, from the Sunday. Saturn orbits at 9.5 astronomical units. At Saturn's distance, sunlight is roughly 100 times dimmer than it appears from Earth. A person standing on one of Saturn's moons would see the Sun as an extraordinarily bright star rather than the blazing disk we know. Radio signals from the Cassini spacecraft orbiting Saturn took between 67 and 85 minutes to reach Earth. Data from those distant observations arrived on scientists' screens more than an hour after the spacecraft recorded it. Neptune sits at approximately 30 astronomical units, 4.5 billion kilometers from the Sunday. At that distance, sunlight takes over 4 hours to arrive. A spacecraft traveling from Earth to Neptune, as Voyager 2 did, required 12 years to make the journey. 12 years of flight through mostly empty space, past gas giants and their moons, through radiation belts, deeper and deeper, into a solar system that kept revealing how much farther it extended than anyone intuitively expected. Voyager 1 launched in September 1977. As of early 2026, it has been traveling for over 48 years and has reached a distance of approximately 165 astronomical units from the Sunday. That translates to more than 24 billion kilometers. Voyager 1 crossed the boundary of the heliosphere, the bubble of charged particles the Sun pushes outward into surrounding space, in August 2012, becoming the first human-made object to enter true interstellar space. 24 billion kilometers sounds like the edge of everything. It is not even close to the edge of anything. The Oort cloud marks the true outer boundary of the Sun's gravitational dominion. This theoretical shell of icy bodies is believed to surround the solar system in a roughly spherical halo, extending from about 2,000 astronomical units to as far as 100,000 astronomical units from the Sunday. 100,000 astronomical units. That is approximately 1.6 light years. Objects within the Oort cloud take millions of years to complete a single orbit around the Sunday. Comets that fall inward from this remote reservoir and streak past Earth on long elliptical paths may not return for tens of thousands or even millions of years. At Voyager 1's current speed of roughly 61,000 kilometers per hour, the spacecraft would need approximately 300 years to reach the inner edge of the Oort cloud. It would require roughly 30,000 years to pass through the cloud entirely and emerge on the other side. 30,000 years. The entirety of recorded human civilization spans roughly 10,000 years. Voyager would need to fly for 3 times the entire span of human history just to cross one structure within our own solar system. And even after emerging from the other side, it would still not have reached the nearest star. The closest stellar neighbor to our Sun is Proxima Centauri, a dim red dwarf sitting 4.24 light-years away. Light itself, traveling at nearly 1 billion kilometers per hour, needs over 4 years to travel from here to there. Voyager 1, our fastest human-made emissary, would need roughly 73,000 years to reach Proxima Centauri if it were heading in that direction. 73,000 years. The last ice age ended about 11,700 years ago. Voyager would need to fly for more than 6 ice ages, laid end to end, before it reached the nearest star. To feel what that distance means at a human scale, consider a model. If you shrank the Sun down to the size of a golf ball and placed it on a table, Earth would be a grain of fine sand orbiting about 4.5 meters away. Jupiter would be a small pea, circling at roughly 23 meters. Neptune, a slightly smaller object, would orbit at about 137 meters. The Oort cloud would extend outward for roughly 90 kilometers in every direction, a gravitational territory the size of a metropolitan region surrounding one golf ball. And Proxima Centauri, the nearest neighboring golf ball, would sit approximately 1,200 kilometers away. 1,200 kilometers of absolute emptiness between two tiny spheres. That is the interstellar neighborhood. That is how far apart stars actually are. This emptiness defines the solar system's true character. The planets feel like a crowded family when you see them illustrated in textbook diagrams, neatly spaced along colorful orbital lines. Those diagrams compress distances by factors of thousands to fit on a page. In reality, the solar system is almost entirely vacuum. If you threw a dart randomly into the volume of space enclosed by Neptune's orbit, the odds of hitting anything, any planet, any moon, any asteroid, are so microscopically small they are effectively zero. Space is not simply large, it is profoundly, relentlessly, overwhelmingly empty. The solar system is the smallest unit of measurement on the scale we are about to climb. Every distance you just struggle to comprehend, the 150 million kilometers to the Sun, the billions of kilometers to Neptune, the tens of billions to the Oort cloud, all of it collapses into a single invisible point when viewed from the next level up. The gap between our solar system and the nearest star is not a distance your brain was designed to process. 1 light year equals approximately 9.5 trillion kilometers. 4.24 light years to Proxima Centauri translates to roughly 40 trillion kilometers. Written out in full, that number contains 13 digits, and this is the closest star. Everything else is farther. Between stars, the interstellar medium contains roughly 1 atom per cubic centimeter. The air you are breathing right now holds approximately 25 quintillion molecules per cubic centimeter. The difference between those two numbers is so extreme that interstellar space qualifies as a better vacuum than anything ever produced in a laboratory on Earth. Yet this emptiness is not featureless. Vast clouds of molecular hydrogen drift between stars, some stretching dozens of light years across. These molecular clouds are stellar nurseries, regions where gas slowly accumulates under its own gravity until pockets of it collapse, heat up, and ignite nuclear fusion. Every star you have ever seen was born inside one of these clouds. The Sun itself formed roughly 4.6 billion years ago from a collapsing region within such a cloud that no longer exists. The material that became Earth, and eventually became you, was once scattered through interstellar space as atoms of hydrogen, helium, carbon, oxygen, and iron drifting in the void between stars that had already lived and died. The iron in your blood was forged in the core of a massive star that exploded as a supernova billions of years before the solar system formed. The calcium in your bones was produced by a different type of stellar explosion. The oxygen you breathe was fused in the furnace of yet another star. You are not metaphorically constructed from stellar material. You are materially, chemically, atomically built from elements manufactured inside stars and ejected into interstellar space through violent deaths. Stars themselves are enormously diverse. The Sun is a yellow dwarf, a middle-aged, medium-temperature star that will burn steadily for roughly 10 billion years before swelling into a red giant and eventually collapsing into a white dwarf, roughly the size of Earth. It represents the most ordinary category of star imaginable. Red dwarfs are the most common stars in the Milky Way, accounting for roughly 70 to 75% of the entire stellar population. They are small, dim, and cool, with surface temperatures ranging from roughly 3,000 to 4,000 degrees Kelvin. The smallest red dwarfs contain only 8% of the Sun's mass, barely enough to sustain hydrogen fusion in their cores. What they lack in brightness, they compensate for in longevity. A red dwarf burns its fuel so slowly that it can shine for trillions of years, far longer than the current age of the universe. Every red dwarf that has ever ignited is still burning today. Not one has had enough time to die. At the opposite extreme sit the blue supergiants, stars so massive and so hot that they burn through their nuclear fuel in just a few million years. A blue supergiant can contain 50 or even 100 times the mass of the Sun, with surface temperatures exceeding 30,000 degrees Kelvin. Their luminosity outshines the Sun by factors of hundreds of thousands. A single blue supergiant can produce more energy per second than an entire cluster of red dwarfs generates in a year. But their ferocity is their undoing. These stars fuse progressively heavier elements in their cores until they reach iron, at which point nuclear fusion can no longer sustain them against gravitational collapse. The core implodes in a fraction of a second. The outer layers are blasted outward in a supernova explosion that can briefly outshine the entire galaxy containing it. What remains depends on the original mass. Some supernovae leave behind neutron stars, objects so dense that a single teaspoon of their material would weigh roughly 6 billion tons at Earth's surface. The most massive leave behind black holes, regions of space-time where gravity has become so intense that nothing, not even light, can escape. Neutron stars pack roughly 1.5 times the mass of the Sun into a sphere only 12 kilometers across. Their density exceeds 100 trillion times the density of water. Some neutron stars spin hundreds of times per second, emitting beams of radiation that sweep across space like cosmic lighthouses. These are pulsars, and their timing signals are so precise, they rival atomic clocks in accuracy. Others possess magnetic fields 1 trillion times stronger than Earth's, powerful enough to disrupt electronics from enormous distances. These objects, called magnetars, occasionally release bursts of energy so intense that a single flare can compress Earth's magnetosphere even from tens of thousands of light years away. The Milky Way contains an estimated 100 million to 1 billion neutron stars and perhaps 100 million stellar mass black holes, all remnants of massive stars that lived and died over the galaxy's 13 billion year history. These objects drift through the galactic disk and halo, invisible unless they interact with nearby matter. You could pass within a few light years of a black hole and never know it was there. The galaxy is a recycling engine. Stars form from gas, burn for millions or billions of years, eject enriched material back into space when they die, and that material is gathered up again by gravity into the next generation. Each successive generation of stars contains a slightly higher proportion of heavy elements than the last. This is why planets like Earth can exist. The first generation of stars, formed from the nearly pure hydrogen and helium left over from the Big Bang, could not have hosted rocky worlds, because the heavy elements needed to build rock and water did not yet exist in significant quantities. It took billions of years of stellar nucleosynthesis, billions of years of supernovae and stellar winds scattering material into space, before the galaxy's chemical inventory was rich enough to produce a planet capable of supporting complex chemistry and eventually life. Earth is a late generation product. It exists because generations of stars lived and died before the Sun was born. This brings us to one of the most consequential discoveries in recent astronomy. Planets are not rare curiosities. They are everywhere. The Kepler Space Telescope, which operated from 2009 to 2018, detected over 2,700 confirmed exoplanets by monitoring the brightness of more than 150,000 stars and watching for the tiny dips in light caused by planets crossing in front of their host stars. Statistical analysis of Kepler's results led to a remarkable conclusion. On average, every star in the Milky Way hosts at least one planet. Many host several. Rocky worlds in the habitable zone, the orbital region where liquid water could persist on a planetary surface, may number in the tens of billions within our galaxy alone. 400 billion stars, tens of billions of potentially habitable rocky worlds, spread across a structure 100,000 to 200,000 light years in diameter. That diameter represents the visible disk of the Milky Way, though the galaxy does not end where the bright stars thin out. The disk of stars is remarkably flat compared to its width. At the Sun's position, the stellar disk measures roughly 2,000 light years in thickness. The ratio of diameter to thickness makes the Milky Way proportionally flatter than a compact disk. If you scaled the galaxy down to the diameter of a dinner plate, the disk would be thinner than a sheet of paper. This extreme flatness results from the galaxy's rotation. The rotating mass of stars and gas settled over billions of years into a thin plane where matter concentrates most densely. The Sun orbits the galactic center at a distance of roughly 26,000 light-years, placing us approximately halfway between the core and the outer edge of the visible disk. We occupy one of the galaxy's spiral arms, specifically a structure called the Orion Arm, or local spur, which branches between the larger Perseus Arm and the Sagittarius Arm. Our position is not special. It is suburban. We live in a galactic neighborhood, neither densely packed near the core, nor sparsely populated in the outer reaches, but somewhere in between, where stars are spaced a few light years apart, and the night sky contains enough visible stars to inspire wonder. The galactic center, by contrast, is a place of extraordinary density and radiation. Stars near the core are packed thousands of times more tightly than in our neighborhood. If Earth orbited a star near the galactic center, the night sky would blaze so brightly with nearby suns that true darkness would never fall. You could read a book by starlight alone, but that brilliance would come with danger. Stellar encounters would be more frequent. Gravitational perturbations could destabilize planetary orbits. Radiation from nearby supernovae and from the central black hole would bathe everything in lethal energy. At the very center of the Milky Way sits Sagittarius A star, a supermassive black hole with a mass of roughly 4 million times that of our Sunday. This object was confirmed through decades of careful observation. Astronomers tracked individual stars orbiting the galactic center and measured their trajectories with extraordinary precision. One star, designated Stu, completes an orbit around Sagittarius A star every 16 years, reaching speeds of roughly 2% of the speed of light at its closest approach. The only object massive enough and compact enough to produce those orbital velocities without being visible is a black hole. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, showing the glowing ring of superheated gas swirling around the black hole's shadow. The image confirmed what decades of indirect evidence had established. Despite its enormous mass, Sagittarius A star is surprisingly quiet compared to supermassive black holes in other galaxies. Some galactic centers are active, blasting jets of material thousands of light years into space and outshining all the stars in their host galaxy combined. Sagittarius A star is dormant, consuming very little material at present. Observations of structures called Fermi bubbles, enormous lobes of high-energy gas extending above and below the galactic plane, suggest that Sagittarius A star experienced a period of intense activity several million years ago, producing outbursts that sculpted the gas distribution across tens of thousands of light years. The monster is sleeping, but it has not always slept. The galaxy rotates, but not like a solid wheel. Stars at different distances from the center orbit at different speeds in a pattern called differential rotation. The Sun travels around the galactic center at roughly 828,000 kilometers per hour. Even at that extraordinary velocity, one complete orbit takes approximately 230 million years. Astronomers call this period a galactic year. The last time the Sun was at its current position in its orbit, dinosaurs had not yet appeared on Earth. In the entire 4.6 billion year history of the solar system, the Sun has completed only about 20 galactic orbits. The galaxy operates on timescales that make geological ages feel brief. Differential rotation creates the spiral arms. These arms are not permanent structures made of the same stars. They are density waves, regions where stars and gas temporarily bunch together before moving on. Similar to how cars slow and cluster in a traffic jam, even though individual vehicles pass through. New stars form preferentially inside the arms because the higher gas density triggers gravitational collapse. This is why spiral arms glow brighter than the spaces between them. Beyond the bright disk, the galaxy possesses a vast spherical halo, populated by ancient stars, globular clusters, and enormous quantities of dark matter. Globular clusters are dense spherical collections of hundreds of thousands to millions of stars bound together by mutual gravity. The Milky Way hosts roughly 150 known globular clusters, many of which orbit far above and below the galactic plane. These clusters are among the oldest objects in the galaxy, with ages reaching 12 to 13 billion years. They formed when the universe itself was young, before the Milky Way had fully assembled into its current structure. Stellar streams, thread through the halo as well. These ghostly rivers of stars form when the Milky Way's gravity captures and tears apart smaller galaxies, or globular clusters that wander too close. The captured stars stretch into long, thin trails that orbit through the halo for billions of years before fully dispersing. Mapping these streams reveals the gravitational field they move through, and that field extends far beyond the visible disk. Stars in the most distant known streams orbit at distances exceeding 200,000 light-years from the galactic center. Dark matter makes this possible. Roughly 85% of the Milky Way's total mass consists of dark matter, a substance that does not emit, absorb, or interact with light in any detectable way. Its presence is inferred entirely through gravitational effects. Stars in the outer galaxy orbit faster than they should based on the visible mass alone. Without the additional gravitational pull from an enormous invisible halo, those outer stars would escape into intergalactic space. Dark matter provides the missing gravity, forming a spherical halo that encompasses the entire galaxy in an invisible gravitational structure. Estimates place the total mass of the Milky Way at roughly 1.5 trillion solar masses, with the vast majority of that mass residing in the dark matter halo rather than in stars or gas. The bright, beautiful galaxy you see in photographs is the visible component of a structure that outweighs it by a factor of roughly 10. The Gaia Space Observatory, launched by the European Space Agency in 2013, has measured the precise positions and motions of nearly 2 billion stars in the Milky Way. This dataset revealed previously unknown stellar streams, mapped the three-dimensional structure of the spiral arms with new clarity, and confirmed that the galaxy's disk is warped, bending upward on one side and downward on the other, like a record left too long in the sundae. The warp likely results from gravitational interactions with the Large Magellanic Cloud, a satellite galaxy that orbits the Milky Way at a distance of approximately 160,000 light-years. Even at that distance, the Large Magellanic Cloud's gravitational tug is strong enough to distort the shape of the galactic disk. The Milky Way possesses at least 60 known satellite galaxies, with new faint ones still being discovered. The Large and Small Magellanic Clouds are the most prominent, visible to the naked eye from the southern hemisphere as hazy patches of light. Most satellites are tiny dwarf galaxies containing only a few million stars, but their orbits reveal the total gravitational mass they are responding to. Every new satellite discovered pushes the known boundary of the galaxy's gravitational reach a little farther outward. The Milky Way is also a cannibal. It grows by consuming smaller galaxies that wander too close. The Sagittarius dwarf elliptical galaxy is currently being devoured, already stretched into a long stream of stars wrapping around the galactic halo. Within a few hundred million years, it will lose its identity entirely, its stars absorbed into the Milky Way's population. Forensic analysis of the Milky Way's stellar populations using chemical signatures and orbital data has revealed evidence of multiple past mergers. The most significant known event is the Gaia-Enceladus merger, which occurred roughly 10 billion years ago, when a galaxy approximately 1/4 the Milky Way's mass collided and merged with ours. The remnants of that ancient galaxy are detectable today as a distinct population of stars with different chemical compositions and orbital characteristics than stars born natively in the Milky Way. The galaxy was built through billions of years of gravitational accumulation and violent consumption of smaller systems. All of this, the 400 billion stars, the spiral arms, the central black hole, the stellar streams, the dark matter halo, the satellite galaxies being digested, constitutes a single galaxy, one structure among an estimated 2 trillion in the observable universe. The nearest major galaxy, comparable in size to the Milky Way, is Andromeda, sitting approximately 2.5 million light-years away. Light leaving Andromeda tonight began its journey 2.5 million years ago, when the ancestors of modern humans were just beginning to use stone tools on the plains of Africa. Every photon from Andromeda that enters your eye carries information that old. You are not seeing Andromeda as it exists now. You are seeing it as it appeared before our species existed. 2.5 million light-years is the distance to our nearest large neighbor. That gap is roughly 10 times the diameter of the Milky Way itself. The entire Milky Way, with all 400 billion of its stars, could be placed in that gap approximately 12 times over with room to spare. Andromeda is falling toward us. The Milky Way and Andromeda are locked in a mutual gravitational embrace that has been pulling them together for billions of years. Andromeda approaches at roughly 400,000 kilometers per hour, closing the 2.5 million light-year gap with the patience of cosmic time. In approximately 4 to 5 billion years, the two galaxies will collide. Their spiral arms will distort. Their halos of dark matter will interpenetrate. Hundreds of billions of stars will rearrange themselves over the course of a billion years into a single massive elliptical galaxy that astronomers have preemptively named Milky Way. Individual stellar impacts will be extraordinarily rare because stars are so widely separated. The Sun, if it still exists at that point, will likely survive the merger with its planets intact, flung into a new orbit around the combined galactic center. The violence of a galaxy collision is gravitational, not physical. It reshapes structure without smashing the components. The Milky Way and Andromeda are the two dominant members of a gravitational family called the Local Group. This collection includes more than 80 known galaxies spread across a volume roughly 10 million light-years in diameter. Most members are dwarf galaxies containing only a few billion or even a few million stars each. The Triangulum Galaxy, also called Messier 33, is the third largest member, containing about 40 billion stars and sitting roughly 3 million light-years from the Milky Way. The Local Group is gravitationally bound. Despite the expansion of the universe pushing distant objects apart, the galaxies within the Local Group are close enough and massive enough that their mutual gravity overcomes that expansion. 10 million light-years across, 80 galaxies. This sounds like a substantial community, until you learn what lies just beyond the neighborhood. The Virgo cluster sits approximately 54 million light-years from the Local Group. It contains over 1,300 known galaxies packed into a volume roughly 15 million light-years across. At its heart sits Messier 87, a giant elliptical galaxy harboring a supermassive black hole with a mass of 6.5 billion solar masses, more than 1,000 times the mass of the black hole at the Milky Way center. In 2019, the Event Horizon Telescope produced the first direct image of a black hole using Messier 87's central object as its target, capturing the glowing ring of superheated plasma swirling around its shadow. That image had traveled 54 million light-years to reach us, meaning the light was emitted when the earliest ancestors of modern horses were first appearing on Earth. The Virgo cluster is not just larger than the Local Group. It represents a fundamentally different category of structure. Galaxy clusters are the most massive, gravitationally bound objects in the universe. They contain not only hundreds or thousands of individual galaxies, but also vast quantities of superheated gas called the intracluster medium. This gas, heated to tens of millions of degrees Kelvin by the gravitational energy of the cluster's formation, glows in X-ray wavelengths, and actually contains more mass than all the stars in all the cluster's galaxies combined. The visible galaxies are islands floating in an ocean of invisible hot plasma, and surrounding everything, outweighing it by a factor of roughly 5, sits the cluster's dark matter halo. The total mass of the Virgo cluster, including galaxies, hot gas, and dark matter, reaches approximately 1.2 quadrillion solar masses. That is 1.2 times 10 to the 15th power suns, a number that has stopped meaning anything meaningful to the human brain. The Local Group itself is falling toward the Virgo cluster. Our entire galactic neighborhood, all 80+ galaxies, is being pulled in its direction at roughly 400 kilometers per second. We will never reach it. The expansion of the universe is carrying the Virgo cluster away from us, slightly faster than we are falling toward it. But the gravitational influence of the Virgo cluster is real and measurable. It distorts the motions of every galaxy in our region of space. Galaxy clusters are held together by gravity, but the gravitational well is overwhelmingly dominated by dark matter. In a typical cluster, dark matter accounts for roughly 80% of the total mass. The hot intracluster gas contributes about 15%. The galaxies themselves, the brilliant objects that give the cluster its visual identity, account for a mere 5%. The galaxies are decoration. The dark matter is the structure. Gravitational lensing provides the most visually striking evidence for this. When light from a distant galaxy passes near a massive cluster, the cluster's gravity bends the light, distorting and magnifying the background galaxy's image. In some cases, the distortion produces arcs, rings, or multiple images of the same background galaxy arranged symmetrically around the cluster. The amount of distortion reveals the total mass responsible for the bending. When astronomers calculate the mass required to produce the observed lensing effects, they consistently find far more mass than the visible galaxies and hot gas can account for. The missing mass is dark matter. The Bullet cluster, located roughly 3.8 billion light-years from Earth, provides what many physicists consider the single most convincing direct evidence for dark matter anywhere in observational cosmology. This system consists of two galaxy clusters that collided at roughly 16 million kilometers per hour. During the collision, the hot gas from each cluster, which interacts electromagnetically, slammed together and slowed down, piling up between the two clusters. But gravitational lensing maps reveal that the majority of the mass in each cluster passed straight through the collision without slowing down at all. The dark matter components of the two clusters, which interact only through gravity, sailed through each other like ghosts. The result is a system where the visible mass and the gravitational mass are spatially separated. The gas is concentrated in the middle. The dark matter is on the outsides. This separation is essentially impossible to explain without invoking a form of matter that does not interact with ordinary matter except through gravity. At the centers of the largest galaxy clusters sit the most massive galaxies in the universe. These brightest cluster galaxies contain up to several trillion stars and harbor supermassive black holes with masses reaching tens of billions of solar masses. The jets from these black holes can extend hundreds of thousands of light years into the surrounding medium, pumping enormous quantities of energy into the intracluster gas and preventing it from cooling and collapsing to form new stars. This feedback loop between black hole activity and cluster gas dynamics is one of the most active areas of current research in astrophysics. Zoom out further, and the Milky Way, the Andromeda Galaxy, the entire Virgo cluster, all of it, dissolves into a single detail within a vastly larger structure called the Laniakea supercluster. Laniakea was identified and named in 2014 by a team led by astronomer Brent Tully. Laniakea spans roughly 500 million light-years and contains the equivalent mass of approximately 100 million billion suns, distributed across an estimated 100,000 galaxies. The name comes from Hawaiian and translates roughly as immeasurable heaven, which turns out to be only a slight exaggeration. Laniakea was mapped not by counting galaxies, but by tracking their motions. Every galaxy in the universe has a peculiar velocity, a motion through space driven by the gravitational pull of nearby mass concentrations. By measuring the peculiar velocities of thousands of galaxies, Tully's team identified coherent flow patterns where galaxies across enormous volumes of space were all streaming in the same general direction. Laniakea is defined as the volume of space within which all galaxy motions converge toward a single gravitational focal point, called the Great Attractor. This massive concentration of matter, partially hidden behind the dense dust of the Milky Way's plane, pulls everything within Laniakea toward it with a gravitational force that influences galaxy motions across hundreds of millions of light-years. To feel what 500 million light-years means, consider that light traveling from one edge of Laniakea to the other would need 500 million years to make the journey. When that light departed, the most complex life on Earth consisted of simple marine organisms. Fish had not yet evolved. The entire Cambrian explosion, the rise of vertebrates, the age of dinosaurs, the evolution of mammals, and the emergence of human civilization would all occur during that single beam of light's transit across one supercluster. Laniakea borders other superclusters. The Perseus-Pisces supercluster lies adjacent to it. The Shapley supercluster, one of the most massive concentrations of galaxies in the nearby universe, sits roughly 650 million light-years away and exerts its own enormous gravitational pull. Laniakea itself may be falling toward Shapley as part of an even larger flow pattern that astronomers are still working to map. The hierarchy of gravitational structures does not stop at superclusters. It continues upward into the largest patterns of matter distribution the universe contains. If you could somehow step outside the universe and look at the distribution of all matter across billions of light-years, you would not see galaxies scattered randomly through space. You would see a vast interconnected network of filaments, walls, and nodes resembling the structure of a sponge, or the neural connections in a brain, or the pattern of soap bubbles in a foam. This network is called the cosmic web, and it represents the largest scale organization of matter in existence. The cosmic web consists of 4 types of structures. Nodes are the densest regions, the intersections where multiple filaments converge. Galaxy clusters form at these nodes, anchored by enormous concentrations of dark matter. Filaments are long, thread-like bridges of dark matter and gas, stretching between nodes, often spanning hundreds of millions of light-years in length, while maintaining widths of only 10 to 20 million light-years. Walls are vast sheet-like surfaces, where filaments meet to form broad planar structures containing thousands of galaxies arranged in thin layers. And between all of these structures lie cosmic voids, enormous underdense regions where almost nothing exists. The filaments are the highways of the cosmos. Gas flows along them, funneled by dark matter's gravity toward the nodes where galaxy clusters grow. Galaxies form preferentially along filaments, strung out like beads on a string. In early 2025, an international research team using an instrument called MUSE on the European Southern Observatory's Very Large Telescope published an unprecedented, high-definition image of a cosmic web filament connecting two galaxies at a 2 cent, distance corresponding to when the universe was roughly 2 billion years old. The filament stretched approximately 3 million light-years. For the first time, researchers could directly trace the boundary between gas inside galaxies and gas contained within the cosmic web itself. When compared to supercomputer simulations of cosmic structure, the observed filament matched theoretical predictions with remarkable precision. Also in late 2025, a team led by researchers at the University of Oxford identified one of the largest rotating structures ever observed, a thin chain of 14 hydrogen-rich galaxies, embedded within a much larger cosmic filament, roughly 50 million light-years long, and located about 140 million light-years from Earth. The galaxies within this thin strand were found to be spinning in the same direction as the filament itself, far more frequently than random chance would predict. This discovery challenged existing models of how galaxies acquire their rotational motion and suggested that the cosmic web may influence galaxy spin more strongly and over larger scales than previously believed. The European Space Agency's Euclid Space Telescope, launched in July 2023, released its first batch of survey data in March 2025, covering an initial deep field and revealing 26 million galaxies. Within these fields, the large-scale organization of galaxies along the cosmic web was already visible, with clusters connected by filamentary strands of galaxies stretching across billions of light-years of cosmic history. Euclid's mission will ultimately survey a third of the entire sky, measuring the shapes of billions of galaxies over 10 billion years of cosmic time, and constructing a three-dimensional map of dark matter distribution on scales never before achieved. The structures revealed by these surveys are staggering. The Sloan Great Wall stretches approximately 1.4 billion light-years across, consisting of thousands of galaxies arranged in a wall-like formation. Even larger is the Hercules Corona Borealis Great Wall, detected through the clustering of gamma-ray bursts and estimated to span roughly 10 billion light-years. If confirmed at that scale, it represents a structure so immense that light would need more than 1/10 of the current age of the universe to travel from one end to the other. But the structures are only half the picture. The other half is emptiness. Cosmic voids occupy roughly 80% of the universe's volume. These immense underdense regions, typically spanning 100 to 500 million light-years across, contain almost no galaxies. They are the hollow spaces between the filaments and walls, where matter has drained away under gravity's patient influence over billions of years. The Boötes void, discovered in 1981, stretches approximately 330 million light-years in diameter and contains fewer than 60 known galaxies. If the Milky Way sat at the center of the Boötes void, the nearest large galaxy would be so distant it would appear as a faint smudge, detectable only through powerful telescopes. The night sky would be vastly emptier than what we see from our current position in the cosmic web. Dark energy, which appears to maintain constant density regardless of how much space expands, dominates voids completely. With so little matter to resist expansion, voids grow faster than the cosmic average, inflating and pushing their boundaries outward into the surrounding filaments. The cosmic web is slowly dissolving, its delicate structure being stretched apart by the relentless pressure of dark energy. Voids are getting larger, filaments are getting thinner. The origin of all this structure traces back to the first moments after the Big Bang. During the epoch of cosmic inflation, in the initial fraction of a second, quantum fluctuations in the density of the primordial plasma were stretched to macroscopic scales. These fluctuations were extraordinarily tiny, variations of roughly 1 part in 100,000. But they were enough. Regions with slightly higher density attracted slightly more matter through gravity. Regions with slightly lower density lost matter to their denser neighbors. Over hundreds of millions of years, this process amplified. Dense regions collapsed into the first stars, which gathered into galaxies, which clustered into groups, which aligned along filaments. Underdense regions emptied further, expanding into voids. The cosmic web is the final product of gravitational amplification acting on quantum noise for 13.8 billion years. The largest structures in the visible universe grew from the smallest fluctuations physics allows. The cosmic microwave background radiation provides a snapshot of those fluctuations when the universe was just 380,000 years old. Satellites, including COBE, WMAP, and Planck, mapped tiny temperature variations across the entire sky, revealing the seeds of all future structure. Scientists feed these measured patterns into supercomputer simulations that model how gravity, dark matter, dark energy, and ordinary matter interact over billions of years. The resulting simulated universes produce cosmic webs that match the observed one with impressive fidelity. Filaments form in the simulations at the same scales and densities as real filaments. Voids open up with the same sizes and emptiness. Galaxy clusters emerge at the nodes with comparable masses and temperatures. This agreement between theory and observation is one of the great triumphs of modern cosmology. But the agreement is not perfect. Some observed structures appear larger or more extreme than simulations comfortably produce. The Hercules Corona Borealis Great Wall, if its size is confirmed, pushes the limits of what standard cosmological models predict. Supervoids estimated at nearly 2 billion light-years in diameter and showing significant density deficits are rare enough in simulations that their existence raises questions about whether our models fully capture the range of cosmic structure. These tensions are not crises. They are frontiers, places where observation pushes theory to evolve and improve. The Dark Energy Spectroscopic Instrument is currently conducting the most ambitious three-dimensional map of the cosmic web ever attempted, measuring precise distances to tens of millions of galaxies and quasars. Its early results, released in stages beginning in 2024, have already produced the most detailed picture yet of how cosmic expansion has evolved over the past 11 billion years. Combined with Euclid's wide-field imaging and the James Webb Space Telescope's deep spectroscopy, these surveys are converging on a comprehensive understanding of how the cosmic web grew from primordial seeds into the vast structure we observe today. All of this, the solar system, the galaxy, the local group, the Virgo cluster, the Laniakea supercluster, the cosmic web itself spanning billions of light years, exists inside a finite volume of space, defined by how far light has traveled since the universe began. Beyond that boundary lies more universe, potentially infinitely more, that we have never seen and may never see. The observable universe has a diameter of approximately 93 billion light-years. That number requires careful unpacking because it contains one of the most commonly misunderstood aspects of modern cosmology. The universe is 13.8 billion years old. Light has been traveling since the cosmos became transparent to radiation, roughly 380,000 years after the Big Bang. You might reasonably expect that the farthest thing we could possibly see is 13.8 billion light-years away. But the universe has been expanding throughout that entire time. Objects that emitted light 13.8 billion years ago were much closer to us when that light began its journey. During the billions of years that light has been traveling toward Earth, the expansion of space has been carrying those objects farther and farther away. By the time their ancient photons finally reach our telescopes, the objects themselves have been swept outward to a current distance of approximately 46.5 billion light-years. Double that to account for the opposite direction, and you get the full diameter of 93 billion light-years. The observable universe is vastly larger than the age of the universe naively implies, because space itself has been stretching while the light was in transit. This observable sphere is centered on Earth, not because Earth is special, but because the observable universe is defined by the observer's location. Every point in the cosmos has its own observable sphere centered on itself. An astronomer on a planet in the Andromeda Galaxy would have a slightly different observable volume, overlapping with ours in most directions, but extending 2.5 million light-years farther in one direction and falling the same amount short in the other. Every observer sits at the center of their own visible cosmos. This is not a privilege. It is a geometric inevitability of finite light speed in an expanding universe. Within this sphere, current estimates place the total number of galaxies at roughly 2 trillion. Each of those 2 trillion galaxies contains anywhere from a few million to several trillion stars. Summing across the entire observable volume produces a total stellar population on the order of 10 to the 24th power. That is 1 septillion stars, written as a 1 followed by 24 zeros. There are more stars in the observable universe than grains of sand on every beach, in every desert, on every seafloor, across the entire surface of Earth. In January 2026, astronomers confirmed that a galaxy designated MOM-Z14, discovered using the James Webb Space Telescope, is the most distant galaxy ever spectroscopically verified. Its light reveals the universe as it appeared just 280 million years after the Big Bang, corresponding to a redshift of 14.44. The galaxy is currently located approximately 33.8 billion light-years from Earth due to cosmic expansion during the intervening eons. It is brighter, more compact, and more chemically enriched than theoretical models predicted for galaxies forming so soon after the origin of the universe. Its existence, along with roughly 100 times more luminous early galaxies than standard cosmology anticipated, suggests that star formation in the infant universe was far more vigorous and efficient than scientists expected. The James Webb Space Telescope has not just pushed back our observational frontier. It has revealed that the early universe was assembling complex structures with a speed that challenges the models we built to explain it. The farthest boundary of our observable volume is not marked by distant galaxies. It is marked by a wall of light. The cosmic microwave background radiation is the oldest electromagnetic signal in existence. Released when the universe was approximately 380,000 years old and had cooled enough for the first stable atoms to form, this primordial light now arrives at Earth from every direction, stretched by 13.8 billion years of cosmic expansion into microwave wavelengths with a temperature of approximately 2.725 degrees above absolute zero. It is extraordinarily uniform. In every direction astronomers look, the temperature is the same, to within a few hundred thousandths of a degree. This uniformity tells us that the early universe was almost perfectly smooth, with only the faintest ripples of density variation seeded by quantum fluctuations during inflation. Those ripples, mapped in exquisite detail by the Planck satellite, encode the initial conditions from which all cosmic structure eventually grew. Every galaxy, every cluster, every filament of the cosmic web traces its ancestry to the pattern of infinitesimal temperature variations in this ancient radiation. No electromagnetic telescope can see beyond it. Before the universe became transparent, no light was free to travel, so no images of earlier epochs can ever be captured using photons. The first 380,000 years of cosmic history are permanently hidden behind this wall of ancient radiation. Other observational windows may eventually pierce this barrier. Gravitational waves generated during inflation could carry information from even earlier moments. Neutrinos decoupled from matter about 1 second after the Big Bang, far earlier than photons, and a cosmic neutrino background should exist, though detecting it remains far beyond current technological capability. Beyond the observable universe lies more universe. How much more is a question that current physics can constrain but cannot definitively answer. The most rigorous approach uses measurements of the spatial curvature of the cosmos. If the universe is curved like the surface of an enormous sphere, then very distant triangles drawn in space would have angles summing to slightly more or slightly less than 180 degrees, depending on whether the curvature is positive or negative. Measurements from the Planck satellite show that space is flat to within the precision of our instruments. This flatness implies that the universe is either infinite or vastly larger than the observable portion. Statistical analyses based on Planck data suggest that the total universe is at least 250 times larger in radius than the observable volume, corresponding to a minimum diameter of roughly 23 trillion light-years. If that lower bound is correct, the observable universe occupies less than 1 part in 15 million of the total cosmic volume. For every galaxy we can see, at least 15 million more exist beyond our horizon, and that is the conservative estimate. The true universe could be substantially larger, possibly infinite. If the universe is infinite, it contains an infinite number of galaxies, an infinite number of stars, and an infinite number of planets. In an infinite cosmos where physical laws and constants are uniform, every configuration of matter that is physically possible must occur somewhere. This includes configurations identical to our own solar system, our own planet, our own civilization. In a truly infinite universe, there must be regions of space where the arrangement of atoms mirrors the exact conditions that form you at this very moment. The implications of infinity are not just strange. They are genuinely disorienting in ways that no smaller number can produce. Whether the universe is infinite or merely unimaginably vast, the portion beyond our observable horizon is permanently inaccessible. This is not a limitation of technology. It is a limitation imposed by the laws of physics themselves. The universe is expanding, and that expansion is accelerating. In 1998, two independent teams studying distant Type Ia supernovae discovered that the expansion of the universe is not slowing down under the braking influence of gravity. As most physicists expected, it is speeding up. Something is pushing space apart with increasing vigor. That something, labeled dark energy for lack of a better understanding, constitutes approximately 68% of the total energy content of the universe. Dark matter makes up about 27%. Ordinary matter, the atoms and molecules that build stars and planets and people, accounts for roughly 5%. The universe is overwhelmingly composed of substances we can detect only through their gravitational effects, and whose fundamental nature remains one of the deepest unsolved problems in physics. Dark energy's accelerating push has a consequence that plays out across cosmic time with quiet but decisive finality. Galaxies beyond a certain distance are currently receding from us faster than the speed of light. This does not violate Einstein's relativity, because the galaxies are not moving through space faster than light. Space itself is expanding, carrying them along, but the practical result is the same. Light emitted by those galaxies today will never reach us. They are beyond our causal horizon. We can neither observe them, communicate with them, nor be influenced by them in any way. And the number of galaxies crossing this threshold grows with every passing moment. The accelerating expansion is gradually shrinking the pool of cosmic neighbors with which we can ever have any physical interaction. In approximately 100 billion years, if dark energy continues behaving as current measurements indicate, every galaxy beyond the local group will have receded beyond the cosmic event horizon and redshifted into invisibility. A civilization arising in that far future epoch would look out into the sky and see only the merged remnant of the Milky Way and Andromeda, a single giant elliptical galaxy surrounded by a handful of gravitationally bound satellites. Within 1 trillion years beyond that, even the cosmic microwave background would have stretched to wavelengths too long for any conceivable instrument to detect. The evidence for the Big Bang, for cosmic expansion, for the existence of other galaxies would have vanished. Those future astronomers, no matter how brilliant, would have no observational basis for concluding that a larger universe existed. They would inhabit a cosmic dark age, isolated in a single galaxy, with the true nature of the cosmos permanently hidden from them by the expansion of space itself. We happen to exist during a brief window in cosmic history, when the evidence is still visible. The cosmic microwave background still glows faintly in our instruments. Distant galaxies still send photons that arrive at our detectors after journeys of billions of years. The large-scale structure of the cosmos is still imprinted in galaxy surveys and gravitational lensing maps. We can still piece together the story. This window will not last on cosmic timescales. The universe is slowly erasing its own history, pulling the evidence beyond reach, one galaxy at a time. Now stand back and consider the full journey. You started as a 1.8 meter figure on the surface of a planet, 12,756 kilometers wide. That planet orbits a star 150 million kilometers away. That star is one among 400 billion in a galaxy 200,000 light years wide. That galaxy is one of more than 80 in a local group 10 million light years across. That group belongs to a supercluster 500 million light years in extent. That supercluster is threaded into a cosmic web of filaments and voids spanning billions of light years. And all of it, every filament, every void, every galaxy, every star, every planet, every atom, exists inside an observable sphere, 93 billion light years in diameter, that may represent less than 1 part in 15 million of the total universe. Each of those steps followed the same pattern. A scale that seemed unfathomably large was revealed to be negligibly small inside the next one. The solar system, which took decades for our fastest spacecraft to partially traverse, vanished to a point within the galaxy. The galaxy, with its hundreds of billions of stars and trillions of solar masses, became a single luminous dot within the local group. The local group dissolved into a minor feature of the Virgo cluster. The Virgo cluster shrank to one node among millions in the cosmic web. And the cosmic web, the largest structure we can map, fits inside an observable volume that may itself be an atom-sized fraction of the whole. This is the central truth about cosmic scale, and it is more radical than simply saying the universe is big. the universe is recursively humbling. Every frame of reference you adopt, no matter how vast, turns out to be a tiny detail inside a larger frame you have not yet considered. There is no scale at which you can stop and say, now I have reached the level that matters. Every level is simultaneously enormous from below and insignificant from above. The solar system is vast beyond human experience and irrelevant on galactic scales. The galaxy is colossal on galactic scales and invisible on cosmic scales. The observable universe is the largest thing we can measure, and it may be an infinitely small fraction of what exists. Our brains evolved to navigate a world of footsteps and throwing distances. We can stretch our intuition to encompass continents and oceans with effort. Beyond that, numbers become abstractions. The distance to the moon is a number. The diameter of the galaxy is a number. The size of the observable universe is a number. But none of these numbers connect to any physical sensation your brain can generate. You cannot feel the emptiness between galaxies. You cannot sense the curvature of cosmic filaments. You cannot intuit the 13.8 billion year journey of a photon from the cosmic microwave background. The numbers exist in your mind as pure data, unanchored to experience, ungrounded in anything your body has ever encountered. And yet here you are, a temporary arrangement of atoms on the surface of a small planet, orbiting an ordinary star in the suburbs of one galaxy among 2 trillion. Your body is built from elements forged inside stars that exploded before the solar system existed. Every atom in your body, heavier than hydrogen, was manufactured inside a star that no longer exists. Those atoms were expelled into space through explosions and stellar winds, drifted through interstellar clouds for millions of years, and were eventually swept up by gravity into the collapsing disk of gas that became our solar system. You did not merely come from the universe. You are the universe, rearranged into a pattern that became capable of contemplating itself. The same laws of physics that govern the expansion of cosmic voids and the collapse of galaxy clusters also govern the electrochemical signals firing in your neurons as you process these words. Gravity shaped the cosmic web. Nuclear fusion built the elements. Chemistry assembled the molecules. Biology organized the cells. And consciousness emerged from that biological complexity, a phenomenon so improbable that we have found evidence of it in exactly one location in the entire observable universe, and yet so powerful that it can reconstruct the history of that universe from fragments of ancient light. A species that evolved roughly 70,000 generations ago on a patch of African grassland has built instruments capable of detecting photons from 13.5 billion years in the past. It has mapped the distribution of invisible matter across billions of light years. It has photographed the shadow of a black hole in another galaxy. It has measured the faint glow of the primordial fireball that filled the universe before any star existed. It has landed machines on other worlds, detected gravitational waves from colliding neutron stars, and confirmed that the expansion of the cosmos is accelerating under the influence of a force it does not yet understand. That last fact bears repeating. We do not understand 68% of the energy in the universe. We cannot directly detect 85% of the matter. We cannot observe more than a small fraction of the total cosmic volume. Our most successful theory of particle physics is known to be incomplete. Our best model of cosmic evolution contains parameters we measure but cannot derive from first principles. We are, by any honest accounting, profoundly ignorant about the fundamental nature of the reality we inhabit. But we know more today than we did yesterday. The Euclid telescope is building the largest three-dimensional map of cosmic structure ever assembled, with its first major cosmology dataset expected in October 2026. The James Webb Space Telescope is pushing the observational frontier toward the era of the very first stars. The Dark Energy Spectroscopic Instrument is measuring the expansion history of the universe with unprecedented precision. Gravitational wave observatories are opening entirely new channels of cosmic observation. Each of these instruments will refine our understanding, correct our errors, and reveal new layers of structure and complexity that we have not yet imagined. The true scale of the universe does not diminish human significance in the way people often assume. The common reaction to cosmic scale is a sense of futility. We are small, therefore we do not matter. But that conclusion does not follow from the evidence. Smallness is a spatial measurement. Significance is not. A single mutation in a genome can alter the course of a species. A single equation written down can redirect the technological trajectory of a civilization. The relationship between physical size and importance is not the linear one our intuition suggests. What the true scale of the universe actually reveals is something more extraordinary. It reveals that the cosmos is structured in a way that permits, across billions of years and billions of light years, the emergence of organized complexity. From initial simplicity, quantum fluctuations became cosmic structure. Hydrogen became stars. Stars became heavy elements. Heavy elements became rocky worlds. Chemistry became biology. Biology became minds capable of reconstructing this entire chain of events from observations made on the surface of one small planet. The scale of the universe is not a statement about human irrelevance. It is a statement about the depth and richness of the physical processes that produced us. The journey from quantum noise to conscious observation required every one of those billions of light years and every one of those billions of years. The vastness is not incidental. It is the mechanism. You are sitting on a rock 12,000 kilometers wide, orbiting a star that is one of 400 billion inside a galaxy that is one of 2 trillion within an observable volume that may be 1/15,000,000th of the whole. Every scale you thought was the biggest turned out to be a rounding error inside the next one. The numbers are real, the distances are physical, and none of it, not a single light year, is wasted. Because somewhere in that incomprehensible expanse of space and time, the universe did something that no amount of emptiness can diminish. It woke up, looked around, and began to measure itself. What scientists still do not know remains, in many ways, more significant than what they do know. The nature of dark matter has been inferred from its gravitational effects for decades, but its constituent particles have never been directly detected. Dozens of candidate particles have been proposed, from weakly interacting massive particles, to axions, to primordial black holes. So far, no confirmed detection has been made. Dark energy is even more mysterious. The simplest theoretical interpretation associates it with the energy density of empty space, a cosmological constant that Einstein introduced and then dismissed as his greatest blunder. But whether dark energy is truly constant, or whether it varies across space and time, is precisely what the Euclid mission and the Dark Energy Spectroscopic Instrument are designed to test. The question of whether life exists elsewhere in the observable universe remains unanswered, but is now being actively investigated in ways that were impossible even a decade ago. The James Webb Space Telescope has begun examining the atmospheres of rocky exoplanets for chemical signatures. The detection of biosignature gases, combinations of atmospheric chemicals that are difficult to explain without biological processes, would be among the most consequential scientific discoveries in human history. Such a detection has not yet been made, but the instruments to make it are now operating, and the number of worlds being examined is growing every year. The origin of the cosmic web itself, rooted in quantum fluctuations stretched to cosmic scales during inflation, is well supported by multiple independent lines of evidence. But the physics of cosmic inflation, what drove it, what stopped it, and what came before it, if anything came before it, remains one of the deepest open questions in theoretical physics. Some physicists have proposed that inflation was not a unique event, that it continues in different regions of a larger multiverse, and that our observable universe is one bubble among an enormous or infinite number of others, each with potentially different physical constants. This idea is currently impossible to test observationally, but the detection of primordial gravitational waves, a major goal of current and future experiments, could provide indirect evidence for inflation and constrain its theoretical models. The cosmic story is not finished. It is barely at the point where the instruments are powerful enough to begin reading it accurately. The next decade of observations from telescopes on the ground and in space will likely revise our understanding of how the cosmic web formed, how fast the universe is expanding, what dark energy is, and what the earliest galaxies looked like in their infancy. Every new dataset will either confirm what we think we know or reveal that we were wrong in ways we had not anticipated. Both outcomes advance the science. The universe is 13.8 billion years old, 93 billion light years across in the observable portion, and composed overwhelmingly of substances we cannot see, governed in its large-scale dynamics by a force we cannot explain, and extending in total extent to dimensions our mathematics can address, but our instruments may never reach. After every measurement, every survey, every space telescope launched, and every simulation run, the honest scientific conclusion is the same one that emerges from the whole journey through scale. There is vastly more to understand than we currently understand, and the process of understanding it is one of the most extraordinary things that has ever happened in this universe. To understand why the measurements matter as much as they do, it helps to trace how our picture of cosmic scale has changed over time. For most of human history, the universe was thought to be small. Ancient astronomers looked at the night sky and saw a fixed dome of stars arranged in patterns that repeated with reliable precision. Those patterns served navigators, farmers, and priests. The stars were understood as signs and symbols, permanent features of the world above. The distances to them were not a serious object of inquiry, because the conceptual tools to think about distances that large did not yet exist. The first major shift came when astronomers began to realize that the Earth moves, not in a philosophical or theological sense, but literally, physically moves around the Sunday. This implied immediately that the stars were not pinpricks in a dome a short distance overhead. If Earth moves through space, in a large orbit around the Sun, then stars nearby should appear to shift slightly in position over the course of a year as we observe them from different vantage points, the same way a nearby tree appears to shift against a distant hillside when you move your head. This apparent shift is called parallax. When astronomers measured it for the nearest stars in the 1800s, the distances they calculated were staggering. 61 Cygni, one of the first stars whose distance was measured by parallax, turned out to be roughly 11 light-years away. This single measurement demolished the ancient picture of the cosmos. If the nearest stars were already 11 light-years distant, then the faint band of the Milky Way stretching across the night sky must represent an almost incomprehensible number of stars at even greater distances. But how great? The Milky Way remained the entirety of the known universe well into the 20th century. Even many professional astronomers in 1920 assumed that all the spiral nebulae visible in telescopes were structures within the Milky Way itself. The idea that they might be separate galaxies, comparable in size and star count to the Milky Way, but located at distances of millions of light-years, was deeply controversial. The debate was settled in the 1920s by Edwin Hubble, working at the Mount Wilson Observatory in California. Hubble identified a class of variable stars called Cepheids in the Andromeda Nebula, and used their known relationship between pulsation period and intrinsic brightness to calculate the distance. The result placed Andromeda far beyond the edges of the Milky Way. The spiral nebulae were not features of our galaxy. They were entire separate galaxies, island universes, and the Milky Way was just one among many. This discovery expanded the known size of the universe by a factor of millions almost overnight. But even this was not the end. Hubble went on to discover that galaxies more distant than Andromeda were moving away from us faster than nearby ones, with recession speed proportional to distance. This relationship, now called the Hubble-Lemaitre law, meant that the universe was not static. It was expanding, and if it was expanding now, then running the clock backward implied that everything in the observable cosmos originated from an extremely hot, extremely dense state, roughly 13.8 billion years ago. This was the Big Bang, which is a misleading name in one important respect. It was not an explosion of matter into pre-existing space. It was an expansion of space itself, carrying matter along with it. Space did not exist before the Big Bang. Time did not exist before the Big Bang, at least not in any form accessible to our current theoretical tools. The universe did not appear inside something larger. It is the something larger. Everything that exists, every particle and every force and every dimension of space and time originated from that initial state and has been evolving ever since. What emerged from the earliest moments was almost pure hydrogen and helium, with trace amounts of lithium. There was no carbon, no oxygen, no iron, no silicon, none of the elements needed to build a rocky planet, an ocean, or a living cell. Those elements had to be manufactured, and the factories that made them were stars. The first stars formed when the universe was a few 100 million years old, condensing from vast clouds of hydrogen and helium under the pull of gravity. These first-generation stars were likely far more massive than most stars today, because the gas from which they formed had not yet been enriched with heavier elements. Heavy elements in a gas cloud can radiate away energy, allowing it to cool and fragment into smaller, lower-mass clumps. Without them, the clouds remained hotter and formed fewer, more massive stars. These massive first stars burned through their fuel quickly and exploded as supernovae, seeding the surrounding gas with carbon, oxygen, silicon, iron, and the other elements that would be essential for everything that came later. This process of chemical enrichment took time. Billions of years passed before the galaxy's interstellar gas was enriched enough to produce rocky planets with complex chemistry. The Sun, which formed 4.6 billion years ago, is a third-generation star or later, meaning the gas cloud from which it formed had already been enriched by multiple previous cycles of stellar birth and death. Earth, and everything living on it, is made from this accumulated inheritance. The timeline of this process is worth sitting with. The universe is 13.8 billion years old. The Sun and Earth formed 4.6 billion years ago. Simple life appeared on Earth roughly 3.5 to 4 billion years ago, within a few hundred million years of the planet's formation. Complex multicellular life did not emerge until roughly 600 million years ago, and anatomically modern humans have existed for only about 300,000 years. The entire span of recorded history, everything from the earliest writing systems to the present, occupies less than 10,000 years. On the timeline of the universe, 10,000 years is approximately 1/1400,000th of the total elapsed time. If you compressed the entire history of the universe into a single calendar year, beginning at midnight on January 1st, the formation of the solar system would occur in early September. Life would first appear on Earth in mid-September. The Cambrian explosion, with its sudden proliferation of animal body plans, would occur on November 17th. The asteroid impact that ended the dinosaurs would arrive on December 26th. Every human civilization that has ever existed would occupy the final 12 seconds before midnight on December 31st. We are a very recent development, but a development that has, in those final 12 seconds, managed to reconstruct the first 13.8 billion years of the story in extraordinary detail. The instruments that have made this possible represent one of the most remarkable technological achievements in the history of science. The Hubble Space Telescope, launched in 1990, spent over 3 decades observing the universe from above Earth's distorting atmosphere. Its deepest images, taken by pointing at tiny patches of seemingly empty sky for days at a time, revealed thousands of galaxies in each field, demonstrating that the universe is filled with structure at every scale the telescope could resolve. The Hubble Deep Field images from 1995 and the Hubble Ultra Deep Field from 2004 transformed our understanding of galaxy evolution, showing that galaxies in the distant universe look different from those nearby, confirming that they had changed significantly over cosmic time. The James Webb Space Telescope, which began science operations in 2022, operates primarily in infrared wavelengths, allowing it to observe galaxies that have been redshifted beyond the range of Hubble's detectors. Its observations have pushed our view of the universe to within a few 100 million years of the Big Bang, revealing that galaxies were forming stars rapidly and efficiently far earlier than models expected. Every new observation from Webb refines or challenges existing theories of galaxy formation, and the instrument still has years of planned observations ahead of it. Ground-based telescopes have also contributed enormously. The Sloan Digital Sky Survey, which operated from 2000 through the 2010s, systematically mapped hundreds of millions of galaxies and quasars, producing the most comprehensive three-dimensional map of cosmic structure available before the current generation of instruments. The patterns revealed by that survey, the filaments and voids and clusters of the cosmic web, provided direct observational confirmation of predictions that cosmological simulations had been making for decades. The Atacama Large Millimeter Array in Chile, an array of 66 radio antennas spread across the high-altitude desert of the Atacama, observes the universe at millimeter and submillimeter wavelengths, allowing it to study cold gas and dust in nearby galaxies, probe the atmospheres of exoplanets, and examine the earliest and most distant galaxies in ways that complement the infrared and optical capabilities of space telescopes. Gravitational wave observatories, specifically the LIGO detectors in the United States and the Virgo detector in Europe, opened an entirely new observational window on the universe in 2015, with the first direct detection of gravitational waves from a pair of merging black holes. Since then, dozens of additional detections have revealed a population of merging compact objects, black holes and neutron stars, whose existence and properties are providing new tests of general relativity and new insights into the evolution of massive stars. In 2017, the simultaneous detection of gravitational waves and electromagnetic radiation from a pair of merging neutron stars confirmed that these events are one source of heavy elements, like gold and platinum, adding another chapter to the story of cosmic chemical enrichment. The next generation of gravitational wave detectors, including the proposed laser interferometer space antenna to be launched in the 2030s, would detect gravitational waves from supermassive black hole mergers across the entire observable universe, and potentially from processes occurring in the very early universe, close to the Big Bang itself. The picture of the universe that emerges from all these instruments is one of extraordinary complexity organized at every scale. Quantum mechanics governs the behavior of particles at the smallest scales. General relativity describes the curvature of spacetime by mass and energy. These two theories together underpin almost everything we know about physical reality, but they are incompatible with each other in a mathematical sense. General relativity predicts smooth, continuous spacetime. Quantum mechanics is built on fundamental discreteness and probability. A complete theory of quantum gravity, one that unifies these two frameworks, does not yet exist. This gap in our theoretical understanding is most consequential precisely where the universe was densest, at the moment of the Big Bang and at the centers of black holes. These are the regimes where both theories are needed simultaneously, and where the absence of a unified framework means that our physics breaks down entirely. Physicists have been working on this problem for decades. String theory and loop quantum gravity are among the candidate approaches, but neither has produced experimentally testable predictions that distinguish it clearly from the alternatives. The resolution of this problem, when it comes, will likely reveal features of physical reality that are currently hidden from us entirely, just as the discovery that the universe is expanding revealed dark energy as a necessary component of cosmological models. The discovery of a quantum theory of gravity may reveal new aspects of spacetime itself that change our understanding of what the universe is at the most fundamental level. What we know with confidence is this: the universe is geometrically flat, or very close to it, on large scales. It is composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. It is 13.8 billion years old, began in an extraordinarily hot and dense state, and has been expanding and cooling ever since. Structure formed because tiny quantum fluctuations in the earliest moments were amplified by gravity over billions of years into the galaxies, clusters, filaments, and voids we observe today. The large-scale structure of the cosmos matches, with impressive fidelity, the predictions of models based on these ingredients. And the cosmos contains, within its observable volume, roughly 2 trillion galaxies, 1 septillion stars, and a number of planets so large that writing it out in standard notation would require a line of digits too long to read before the end of a human lifetime. Within all of that, somewhere in the Orion arm of the Milky Way galaxy, on a rocky planet orbiting an unremarkable yellow star at 150 million kilometers, chemistry arranged itself into biology, biology arranged itself into brains, and brains began asking questions about all of it. That conversation between mind and cosmos, between a 3-pound organ and a 93 billion light-year sphere, is where things stand right now. The instruments are running, the data is arriving, the models are being tested and revised. The edge of what is known is moving outward, as it has been doing since the first human tilted their head back on a clear night and wondered what the lights were. The answers we have found so far are not the kind that close the question. They are the kind that reveal how much more there is to ask. Consider more carefully what it means for the universe to have a beginning. 13.8 billion years ago, the observable universe occupied a volume smaller than a proton. All of the matter and energy that now fills 93 billion light-years of space, every galaxy, every star, every photon, every neutrino, every gravitational wave, was compressed into a region of effectively zero size. The temperature was effectively infinite. The density was effectively infinite. The laws of physics, as we understand them, cannot describe the conditions at that singular moment, because the mathematics produces meaningless infinities before it reaches zero time. What we can describe, with increasing confidence, is what happened in the moments immediately after. Within the first second, the universe cooled enough that protons and neutrons could form from the quark-gluon plasma that dominated even earlier. Within the first 3 minutes, nuclear reactions fuse some of those protons and neutrons into helium nuclei and trace amounts of lithium. This process, called Big Bang nucleosynthesis, produced the proportions of hydrogen and helium we observe today throughout the universe, proportions that match theoretical predictions with remarkable precision. That agreement between the calculated and observed helium abundance is one of the strongest pieces of evidence supporting the standard cosmological model. For the next 380,000 years, the universe remained opaque. Photons scattered constantly off free electrons in the hot plasma, unable to travel more than microscopic distances before being absorbed and re-emitted. The universe was foggy with its own light. Then the temperature dropped far enough for electrons to be captured into stable orbits around protons, forming the first neutral hydrogen atoms. The fog cleared. Photons were suddenly free to travel, and they have been streaming through space ever since. Those are the photons we detect today as the cosmic microwave background. The period between this epoch and the formation of the first stars is sometimes called the cosmic dark ages. No stars existed. No light was being generated by any astronomical object. The universe was filled with neutral hydrogen gas, cooling slowly as space expanded, clumping gradually under gravity in patterns seeded by the initial quantum fluctuations. The darkness lasted for roughly 100 million to a few hundred million years. Then the first stars ignited. Hydrogen gas in the densest clumps collapsed under gravity, heated to the temperatures needed for nuclear fusion, and began radiating energy. This light was not gentle. The first stars were massive and luminous, and their ultraviolet radiation began stripping electrons from the surrounding neutral hydrogen gas in a process called reionization. Over hundreds of millions of years, this radiation transformed the intergalactic medium from neutral to ionized, ending the cosmic dark ages and filling the universe with the warm, glowing plasma that still pervades the spaces between galaxies today. Reionization was not a single event, but a gradual process. As the first stars and their descendant galaxies ionized progressively more of the surrounding gas, until the universe became largely transparent to ultraviolet light, sometime between about 500 million and 1 billion years after the Big Bang. The James Webb Space Telescope is actively investigating this period. By observing galaxies in the epoch when reionization was underway, Webb is measuring how early galaxies contributed to the process, and how the transition from a neutral to an ionized intergalactic medium unfolded across cosmic time. The results are already revealing surprises. The galaxies driving reionization appear to have been more numerous, more luminous, and more chemically evolved than theoretical models predicted. After reionization, the broad strokes of cosmic evolution proceeded in the direction we have already traced. Galaxies formed, merged, grew, and evolved. The rate of star formation across the universe peaked roughly 10 billion years ago, when the cosmos was about 3 to 4 billion years old, and has been declining ever since as the available supply of cold gas is slowly consumed and not fully replenished. We live in a universe that is, in terms of star formation activity, past its most productive period. The golden age of star formation is behind us, not ahead of us. This decline in star formation is connected to the interplay between galaxy growth, black hole feedback, and the large-scale environment of the cosmic web. As galaxies grow, the supermassive black holes at their centers grow as well, fed by infalling gas. When a black hole is actively feeding, it releases enormous amounts of energy in the form of radiation and jets of high-speed plasma. This energy heats the surrounding gas in and around the galaxy, preventing it from cooling and collapsing into new stars. The result is that the most massive galaxies, those with the most massive central black holes, tend to shut down their star formation earliest. They become red and dead, populated by aging stars and producing almost no new ones. The Milky Way is intermediate in mass and still forming stars, though at a modest rate of roughly 1 to 3 solar masses per year. The most massive galaxies in the universe, the brightest cluster galaxies at the centers of galaxy clusters, formed most of their stars billions of years ago and have changed relatively little since. The long-term future of the universe, extrapolated from current measurements, is in some ways even more extreme than the history. The expansion of space driven by dark energy will continue indefinitely, assuming dark energy behaves as current data suggest. Galaxies will gradually recede beyond the cosmic event horizon. The local group will persist as a gravitationally bound island in an increasingly empty cosmos. Within the local group, the eventual merger of the Milky Way and Andromeda will produce Milkomeda, a massive elliptical galaxy with little ongoing star formation. Over trillions of years, the remaining stars within Milkomeda will age and die. The most massive stars will already have expired billions of years ago. The Sun will exhaust its hydrogen fuel in roughly 5 billion years, swell to a red giant that may engulf the inner planets, and eventually shed its outer layers into a planetary nebula. leaving a white dwarf behind. That white dwarf will cool for trillions of years, gradually fading from white to yellow to orange to red to black, eventually becoming an invisible dark remnant orbiting the galactic center with no more light to emit. The red dwarfs, the most numerous stars in the galaxy, will outlast everything else. The smallest and dimmest of them, containing barely enough mass to sustain fusion, will burn for 10 trillion years or more before exhausting their hydrogen fuel. After their stars die, galaxies will be populated primarily by stellar corpses, white dwarfs, and neutron stars and black holes, orbiting in a growing darkness. On even longer timescales, the gravitational interactions between stellar remnants in the galactic halo will gradually scatter them outward. Some will be ejected entirely from the galaxy through gravitational encounters. Others will sink toward the central black hole and eventually be swallowed. Over a timescale of 10 to the 23rd power years or more, essentially all stellar remnants will have been either ejected or accreted, leaving only the supermassive black holes as the dominant objects in the universe. Those black holes are not permanent either. Stephen Hawking demonstrated theoretically in the 1970s that black holes slowly lose mass through a quantum process called Hawking radiation. The rate is vanishingly slow for large black holes, the supermassive ones at galactic centers losing mass so slowly that the timescale for them to evaporate completely exceeds 10 to the 100th power years. But evaporate they will, assuming Hawking's analysis is correct and no unknown process stabilizes them. After that, nothing recognizable remains. The universe, if it persists long enough, and if current physics is correct in its broad outlines, will eventually reach a state of maximum entropy, sometimes called the heat death of the universe, in which no thermodynamic processes can occur, no energy gradients remain to drive any work, and the cosmos is a cold, dark, and homogeneous void. This is the long-term trajectory extrapolated from current measurements. Whether it accurately describes the actual fate of the universe depends on whether dark energy remains constant, whether protons are stable on timescales of 10 to the 34th power years or longer, and whether physics as currently understood remains valid across timescales billions of times longer than the current age of the universe. All of these are open questions. What is not open to question is the extraordinary fact that the universe, in the 13.8 billion years it has so far existed, has produced complexity of remarkable depth and diversity from initial conditions of remarkable simplicity. The entire cosmic web, with its filaments and voids and galaxy clusters, grew from density fluctuations smaller than 1 part in 100,000. Every star, every planet, every molecule, every cell, every thought grew from that almost uniform beginning. The universe began as a nearly featureless hot plasma and produced, over billions of years, structures that range in scale from subatomic particles to superclusters spanning 500 million light-years. At one scale, within that enormous range, on a rocky planet orbiting an average star, a specific arrangement of molecules became capable of looking back across that entire history and asking how it all came to be. That question, and the methods developed to answer it, are among the most remarkable things that have emerged from the physical laws governing this universe. Science is, among other things, the universe's way of understanding itself, one measurement at a time. The measurements are still coming in, the telescopes are still running, the data is still being analyzed, and the universe, indifferent to whether anyone is watching, continues to expand in every direction at once, carrying its galaxies and its history, and its open questions outward, into a future that current physics can describe in broad strokes, but cannot yet fully see. The question of what lies beyond the observable universe is not merely philosophical. It has observational implications and theoretical constraints that physicists take seriously. If the universe is truly flat, as the Planck satellite data strongly suggests, then the total universe is either infinite or has a size vastly larger than the observable portion. In an infinite flat universe, the observable bubble we inhabit is one of an infinite number of similar bubbles, each centered on its own observer, each containing roughly 2 trillion galaxies, each measuring roughly 93 billion light-years in diameter. These bubbles overlap partially with adjacent ones, but not fully, because the farthest regions of one observer's bubble are beyond the horizon of another observer a billion light-years away. In an infinite universe of this kind, every possible configuration of matter that is physically consistent with the laws of nature must occur somewhere. The argument is purely probabilistic. There are only finitely many ways to arrange the particles in a volume the size of our observable universe. In an infinite universe, all finite arrangements repeat. Some of those repetitions will be exact duplicates of what exists within our observable volume, including our solar system, our planet, and everything on it. The nearest such duplicate, in an infinite flat universe with the observed matter density, would be located at a distance of approximately 10 to the 10 to the 28th power meters. That number is so large, it makes the observable universe look like a rounding error. But, in an infinite universe, it exists. This is not science fiction. It is a mathematical consequence of combining standard cosmological measurements with an infinite spatial extent. Whether it is physically meaningful is a separate question that depends on interpretational choices about the relationship between mathematical structures and physical reality. The inflationary multiverse hypothesis extends this reasoning. If the universe underwent rapid exponential expansion in its earliest moments, and if this inflation is driven by a quantum field, then quantum mechanics predicts that inflation should be eternal in a global sense. Even if it ends locally in any given region, different regions would stop inflating at different times and potentially settle into different low-energy states, each with different effective physical constants. In this picture, our observable universe is one bubble in a vast or infinite ensemble of bubbles, each with its own internal physical laws. The constants we measure, the masses of fundamental particles, the strength of the fundamental forces, the value of the cosmological constant, may be environmental features of our particular bubble, rather than uniquely determined values. If this picture is correct, then the question of why physical constants have the values they do, a question that has puzzled physicists for decades, receives an anthropic answer. We observe the values that allow for the existence of stable matter, chemistry, and life, because we could not exist to make observations in bubbles with wildly different values. This reasoning is controversial because it cannot currently be tested observationally. A theory that cannot be falsified is not science in the conventional sense, but the inflationary framework that motivates it does make testable predictions about the statistical properties of the cosmic microwave background, and those predictions have held up well against observations. The distinction between what is known and what is speculated is important to maintain clearly. The expansion of the universe is measured. The flatness of space is measured. The composition in terms of dark matter, dark energy, and ordinary matter is measured. The age of the universe is measured. The large-scale structure of the cosmic web is mapped. The history of star formation across cosmic time is charted. These are observational results, not theoretical speculation. The nature of dark matter, the nature of dark energy, the physics of inflation, the total size of the universe, the existence of a multiverse, the possibility of life elsewhere in the cosmos. These are open questions. Some of them are being actively investigated with existing instruments. Others require technology that does not yet exist. Some may be permanently inaccessible. The line between what we know and what we do not know is not fixed. It moves, as it has been moving since the first systematic observations of the night sky. The distances to stars were unknown until parallax measurements made them accessible. The scale of the galaxy was unknown until Cepheid variable stars and distant nebulae were observed from large enough telescopes. The expansion of the universe was unknown until the recession velocities of distant galaxies were measured. The existence of dark energy was unknown until supernova measurements revealed the acceleration of cosmic expansion. The structure of the cosmic microwave background was poorly characterized until satellite observatories mapped it in detail. Each of these advances required new instruments, new techniques, new theoretical frameworks, and in some cases, new conceptual vocabulary. The same pattern will almost certainly continue. The universe has consistently revealed itself to be more complex, more structured, and more surprising than the models that preceded each new observation. There is no principled reason to expect that the next generation of instruments will not produce comparable surprises. The Vera C. Rubin Observatory, currently completing construction in Chile, will conduct a 10-year survey of the southern sky beginning in the mid-2020s, generating the most complete time-domain survey of the visible universe ever assembled. It will detect tens of billions of astronomical objects, track the motions of asteroids and comets in our solar system, map the distribution of dark matter through gravitational lensing, and measure the properties of millions of supernovae across the sky. The sheer data volume it will produce, estimated at roughly 15 terabytes per night, will require new approaches to data analysis and will almost certainly reveal phenomena not yet anticipated by current models. The Square Kilometre Array, an international radio telescope facility being constructed across South Africa and Australia, will observe the universe in radio wavelengths with sensitivity and resolution far exceeding any previous radio observatory. Among its primary science goals is mapping the distribution of hydrogen gas across cosmic time, tracing how the fuel for star formation has moved through the cosmic web and been consumed by successive generations of stars. It will also search for radio signals from potential technological civilizations elsewhere in the galaxy, covering a vastly larger volume of space with higher sensitivity than any previous search. The proposed Laser Interferometer Space Antenna, a gravitational wave observatory consisting of 3 spacecraft flying in a triangular formation tens of millions of kilometers across, would detect gravitational waves at frequencies far lower than ground-based detectors can access. Its primary targets would include merging supermassive black holes in distant galaxies, events that release energy exceeding that of 1 million supernovae in the form of gravitational waves, and potentially the stochastic background of gravitational waves produced during cosmic inflation. If inflation generated detectable gravitational waves, their spectrum would encode information about the energy scale at which inflation occurred, providing a direct observational probe of physics at energies far beyond what any particle accelerator can reach. These instruments represent the next chapter in a tradition of observation and measurement that has been steadily expanding the known universe for centuries. Each generation of instruments has revealed structures and phenomena that the previous generation could not see. There is no compelling reason to think that the next generation will be any different. What is certain is that the universe we inhabit is vastly older, larger, more structured, and more complex than any previous era of human history knew. The measurements are precise, the distances are real. The emptiness between galaxies is genuine. The light from the cosmic microwave background is actual radiation from the edge of the observable universe, released when the cosmos was 380,000 years old. And somewhere, within all of that space and time, on a planet that has existed for 4.6 billion years, organisms that have existed for 300,000 years are using instruments they built in the last century to reconstruct the history of everything. The scale is not just a description of how big the universe is. It is a description of how much has happened, and how much remains to discover. There is a particular kind of cognitive displacement that happens when you follow the scale of the universe carefully, step by step. It is not the same as reading a large number. Reading that the observable universe contains 2 trillion galaxies produces a momentary sense of vastness. Then the mind moves on. The number does not linger. It does not change anything about how you experience the room you are sitting in. What changes when you follow the scale step by step is the frame of reference itself. You begin at the scale of a human body, where your intuition functions properly, and each successive step demolishes the previous frame before you have had time to rebuild your bearings. The Earth seems enormous until the distance to the moon makes it seem small. The distance to the moon seems unimaginable until the distance to the sun makes the moon seem nearby. The distance to the sun seems vast until the distance to the Oort cloud makes the sun seem accessible. The Oort cloud seems like a boundary until the distance to the nearest star makes the Oort cloud seem like a suburb. The nearest star seems impossibly far until the diameter of the galaxy makes interstellar distances seem like footsteps. At every step, the previous scale collapses into insignificance. The collapse is not gradual, it is sudden, like the ground dropping away beneath you. The galaxy felt enormous until the distance to the Andromeda galaxy made the Milky Way seem small. Andromeda seemed impossibly distant until the Virgo cluster made it seem like a neighbor. The Virgo cluster seemed beyond comprehension until the Laniakea supercluster made it seem like a local feature. And Laniakea, 500 million light-years of organized cosmic structure containing 100,000 galaxies, dissolves into a minor node when you zoom out to the scale of the full cosmic web. And the cosmic web, all of it, every filament and void and galaxy cluster, fits inside the observable sphere like a city fits inside a country. Like a country fits inside a planet. Like a planet fits inside a solar system. Like a solar system fits inside the galaxy. Like the galaxy fits inside the universe. Each frame contains the previous one and makes it invisible. This recursive collapse of scale produces a disorientation that is different from simply being told the universe is large. Being told the universe is large is like being told a country has a large population. The number registers and then disappears. Following the scale step by step is more like visiting each level in person. You stand in a village and it seems complete. You rise to see the village is one of hundreds in a valley. You rise further to see the valley is one of thousands in a region. Each ascent reveals a larger structure that the previous view could not see, and the structure you thought you were standing in turns out to have been a detail all along. The universe conducts this exercise across 60 or more orders of magnitude, from the scale of a subatomic particle to the scale of the observable cosmos. No other journey covers that range, and the journey does not end with the observable universe, because what lies beyond it, whether finite or infinite, is larger still. What is perhaps most striking is not the size itself, but the fact that the sizes are knowable at all. The distance to the moon was measured with ancient geometric methods. The distance to the sun was determined through careful parallax observations. The distances to nearby stars were triangulated using Earth's orbit as a baseline. The distances to farther stars were inferred from their intrinsic brightness relative to their apparent brightness. The distances to other galaxies were calculated from the brightness of standard candles. First, Cepheid variable stars, then type Ia supernovae. The age of the universe was measured from the expansion rate and the detailed pattern of temperature fluctuations in the cosmic microwave background. Each of these measurements required ingenuity, patience, technology, and the willingness to follow observations wherever they led, even when the results were surprising. The universe did not reveal its scale because humans assumed it was large. It revealed its scale because humans built instruments sensitive enough to detect the signals that encoded the distances, and then followed the math. The result is a map of reality that spans 60 orders of magnitude and reaches back 13.8 billion years. No single mind can hold that map in full clarity, but the map exists. Its broad contours are established, and every year, new measurements fill in more detail, correct earlier estimates, and reveal structure that no previous instrument could see. The process is not finished. It is not close to finished. The observable universe contains roughly 2 trillion galaxies, and the large majority of them have never been individually studied. The cosmic web has been mapped in rough outline, but not in detail. The nature of dark matter remains undetermined. The nature of dark energy remains unknown. The conditions of the first moments of the universe are accessible only through indirect inference. The question of whether life exists elsewhere is completely open. These are not small gaps. They are the main questions. The science of the very large, cosmology and astronomy at the scale of galaxies and beyond, is in many respects a young field. It acquired most of its current knowledge in the last century, and the pace of discovery has been accelerating as instruments have improved. The next century, with its next generation of telescopes and detectors and computational tools, will almost certainly produce revelations comparable in magnitude to the discovery that the universe is expanding, or the mapping of the cosmic microwave background, or the detection of gravitational waves. What those revelations will be is not predictable in detail. The history of science provides little support for confident predictions about where the next surprises will come from. What it does support is the expectation that surprises will come, and that they will come from wherever the instruments are sensitive enough to see something no previous instrument could see. The universe, after all, is not running out of things to show us. It is running out of nothing. There is structure at every scale, process at every epoch, complexity at every level of organization, from the quantum to the cosmic. The investigable territory is effectively unlimited. The limitation is always on the side of the observers, not on the side of what is there to be observed. And the observers, the temporary arrangements of stellar material that evolve the capacity to look back at the stars they came from, have spent a few thousand years getting better and better at the looking. The scale of the universe is not a problem to be solved or a mystery to be mourned. It is the terrain. It is what exists. And existing within it, with instruments and mathematics and centuries of accumulated knowledge, it is possible to navigate more of that terrain with every generation that passes, one measurement, one observation, one carefully verified fact at a time. One thing that the journey through cosmic scale clarifies is the relationship between time and space at these dimensions. We experience time and space as separate things in daily life. Space is the gap between objects. Time is what passes while we move between them. But at cosmic distances, the two become deeply intertwined, because light takes time to travel. This means that looking out in space is also looking back in time. The farther away an object is, the longer its light took to reach us, and the younger the universe was when that light departed. A star in our own galaxy that is a few thousand light years away appears as it was a few thousand years ago. The Andromeda galaxy, 2.5 million light years away, appears as it was 2.5 million years ago. The most distant galaxies the James Webb Space Telescope has observed are seen as they were over 13 billion years ago, when the universe was only a few 100 million years old. And the cosmic microwave background, the farthest thing we can observe, shows the universe as it was 380,000 years after the Big Bang, nearly 13.8 billion years ago. This means that looking at the sky is looking at a history book. Each layer of distance corresponds to an earlier epoch in the universe's evolution. Nearby galaxies show the present, or nearly so. Distant galaxies show an earlier time when they were younger, more actively forming stars, less chemically enriched, and structured differently. The most distant detectable signals show the universe before any galaxy existed, when the cosmos was a nearly uniform hot plasma. What the combination of all these observations allows is a reconstruction of the universe's full history, from the Big Bang to the present, from a single vantage point in space and time. An observer on Earth today can see 13.8 billion years of cosmic history simultaneously, with each distance corresponding to a different epoch. This is not true of any other kind of science. Geologists must infer ancient conditions from rocks. Paleontologists must reconstruct ancient life from fossils. But cosmologists can observe ancient conditions directly, because the universe has been transmitting its own history in the form of light, and light does not forget where it came from or how long it traveled to get here. The cosmic microwave background is the oldest light. Its uniformity tells us that the early universe was almost perfectly smooth. Its tiny temperature variations, at the level of 1 part in 100,000, tell us about the quantum fluctuations that seeded all future structure. These fluctuations have been magnified by gravity over 13.8 billion years into the galaxies and filaments and voids we observe today. The pattern of those fluctuations encodes information about the total density of the universe, the relative proportions of dark matter and ordinary matter, the rate of expansion, the geometry of space, and the spectrum of primordial density perturbations. Each of these parameters has been measured with increasing precision through successive generations of instruments. The current standard model of cosmology, sometimes called lambda CDM for the cosmological constant representing dark energy and cold dark matter, fits all of the available data with impressive accuracy. Its predictions match the observed properties of the cosmic microwave background, the distribution of galaxies in space, the abundance of light elements from Big Bang nucleosynthesis, and the acceleration of cosmic expansion revealed by supernova observations. This convergence of independent measurements on a single, consistent picture is one of the strongest arguments that the broad outlines of our cosmological understanding are correct. The universe is old, large, expanding, flat, and composed primarily of dark matter and dark energy. These are not guesses. They are conclusions supported by multiple independent lines of observational evidence, each of which would be very difficult to reconcile with any significantly different cosmological model. What remains uncertain is the next layer of detail. Why does dark energy have the value it has? If it represents the energy of empty space, why is it not vastly larger, as naive quantum field theory calculations predict? This discrepancy between the predicted and observed values of the cosmological constant is sometimes called the worst prediction in physics, because the naive calculation overshoots the observed value by something like 120 orders of magnitude. No satisfactory explanation has been found. The observed value may be selected anthropically in a multiverse, but as already noted, that explanation currently has no testable consequences beyond the observations that motivated it. Why is there more matter than antimatter in the universe? The Big Bang should have produced equal quantities of each. Matter and antimatter annihilate on contact. If equal amounts existed, they would have annihilated entirely, leaving a universe of pure radiation and no matter at all. Clearly, the universe contains matter. Something must have produced a slight asymmetry in the very early universe, about 1 extra matter particle per billion matter-antimatter pairs, and that small excess survived the annihilation to become everything that exists. The process responsible for this asymmetry, called baryogenesis, has not been identified. The known laws of physics do not produce enough asymmetry to explain the observed matter content of the universe. These are not small puzzles at the edge of an otherwise complete theory. They are central questions about why the universe has the character it has. A complete understanding of cosmology requires answering them. The program of attempting to answer them will take decades, perhaps centuries, of continued observation, theory, and experiment. It will require instruments we have not yet built, mathematical frameworks we have not yet developed, and conceptual vocabulary we have not yet invented. Each step will build on the previous one, as it has done from the first telescopic observations of Jupiter's moons, to the mapping of the cosmic microwave background temperature fluctuations, to within fractions of a millionth of a degree. The universe is vast. The questions about it are deep. The tools for investigating it are improving, and the investigation is ongoing. That is where things stand, on this particular rocky planet, in this particular orbit, around this particular star, in this particular galaxy, within this particular observable bubble of a universe that is itself possibly an infinitely small fraction of what exists.